Physical science students, welcome. What's happening? Today we're going to take a look at some slides in connection with atomic structure. I know we've taught you what atoms don't look like. We taught you the Bohr's model of the atom, which is great for knowing where protons, neutrons, and electrons are. But now we're going to take a look at, even further back in history, some other ideas that people once thought were what atoms looked like, and we'll work our way forward to what our current understanding of atomic structure actually is. So let's start off way back in the day. 384 BC, we had Aristotle, who thought that everything in the world could be categorized as either earth, wind, water, or fire. What Aristotle actually was onto was really states of matter, right? Solid, liquids, gases, and plasmas. Earth was our solid, water is our liquid, air was our gas, and then fire here was our plasma. And so he didn't understand atoms yet, but he was on to something. Take a look at 460 to 370 BC. We had Democritus, who came up with this idea that everything in the universe was made up of these tiny little building blocks. And he called them atoms, right? And so this was the first idea that maybe there was something smaller that our eyes couldn't pick up on that made up all other matter throughout the world. It wasn't until 1803, look at that huge jump in time, to 1803, when John Dalton finally expanded upon this atomic theory and said, hold on, I like this idea of atoms, but I believe that each individual atom is not the same. We've got different types of atoms, and when you combine them differently, they make other things. So he's sticking with atoms, but he's simply saying that each atom is not identical. They look different, and they, in different combinations, build different things. 1897, we had J.J. Thomson. He was the first one to come up with the idea that the atom itself has parts or different areas. He said there's this positive charge and there's this negative charge. So he came up with what they call the plum pudding model. I like to call it the cookie dough model because I don't remember the last time I had plum pudding, right? In the cookie dough model or plum pudding model, J.J. Thomson says there are these negatively charged areas, and we're calling them electrons. And they're surrounded by this positively charged matter, but he didn't know much about that positively charged matter, and so it's kind of like the chocolate chips in cookie dough are the electrons in this positively charged matter that makes up the atom. So it was a step in the right direction. 1911, Ernest Rutherford does this gold foil experiment. He takes these charged particles and he shoots them at a really thin gold foil. Okay, very thin. And he expected the atoms, for the most part, those charged particles, to pass through those gold atoms and not really be deflected from their path very much. Every once in a while, one of those charged particles would hit the gold foil and come bouncing back. And that was astonishing to him. He, from that, discovered that there must be in the atom a bunch of empty space and then a central core of concentrated matter. And that's where the idea of the nucleus came from. He was so amazed by this, he said it would be like taking a cannonball, essentially, and shooting it at a piece of paper and having the cannonball bounce off the paper. He did not expect to find this concentrated nucleus at the core of the atom. 1922, Niels Bohr. This is where we started as a class. He basically suggested the idea that these electrons that are moving around the outside of the nucleus are doing so in organized ways. His looks a lot like planets moving around the sun, and we know that's not the case, but to him at that time this made a lot of sense, and there's use to it. It shows us where the protons, neutrons, and electrons are. We just now know that the electrons don't move around the nucleus in this organized path. Okay? 1932, James Chadwick comes up with the idea that there's something else in the nucleus of the atom. It's not just this positively charged area, but there are also things in the nucleus that don't have any charge at all, but have mass, and that's where the neutron came about. So he's now giving us more detail about the core or the nucleus of the atom, and still entertaining the idea that these electrons are moving around in these energy levels outside of the nucleus. Now, Erwin Schrödinger, his cat, is an interesting experience. You can go read that one on the internet if you're interested in knowing more about that. He comes up with the quantum mechanical model. And look at how different this looks. He says, we've still got a nucleus, but outside the nucleus, something, please stay with me on this is a crazy idea. Each of these little blue dots is not an electron. As a matter of fact, each of those blue dots represents the same electron. and it is like this cloud shows where that electron could be located, right? The most likely location to find that electron. So one blue dot, okay, or all of these blue dots, I should say, are representing the same one electron, and the dot just shows where it could be. So the quantum mechanical model introduces this idea of probability, right? If you flip a coin, what's the probability of it being heads versus tails, right? Over time, it works out to be about 50%. If you roll dice, what's the probability? How often will you roll a 6? Or your chances are 1 in 6, as long as there's not something fishy with the dice. If you look at, for example, someone's home, you could try and find where are the most probable locations for someone to be located within their home. How often are they in the porch? How often are they in the breakfast nook? How often are they in the living room, right? How often are they in the study? They could be anywhere in the home, but over time you would find that there's a most likely location to find them. For me personally, it's right here in the kitchen, right? Wherever the food is. So the probability of finding an electron somewhere is what the electron cloud or the quantum mechanical model is based off of. We'll talk more about probability another day. That's it for these slides.